Okay, so kind of a strange operation there, and it turns out that there are some surprising things, at least they're surprising to me, about matrix multiplication that don't always align with your intuition because they act differently than the multiplication you grew up and loved in elementary school, right? So let's look at a few of those. One has to do with the dimensions here. So remember, if I'm going to multiply two things together, and one's m by n and the other's p by q, we remember our rules that n has to equal p in order for this to be done, and if it is equal to p, then great, you can do it, and you get an m by q answer, right? Consider what this does if you have a row vector and a column vector. So suppose I say that I've got a row vector x, and it's equal to 1, 5, 2, and let's say I've got a column vector y, and that's equal to 3, 0, 3, right? Now, remember, I talked about row vectors and column vectors, and at times we're going to play fast and loose here, and we're going to treat it as a vector. Sometimes we're going to treat it really as a matrix with only one row or only one column other times. Here, I'm sort of treating it in the matrix way. So if I asked you, what is x dot product or multiplied by y, what you're going to get is you're going to take this thing here, dot producted with this thing here, right? Which is going to give you 3 times 1 plus 0 plus 3 times 2. So I think that's going to be 9. So x dot y is the number 9. Now, what if I said, what's y times x? You might say, well, that's going to be the same thing. Turns out it's not anywhere remotely the same thing. In fact, you get a completely different kind of thing. Because if I take y here and I multiply it by x, which is this row vector, think of what I have to do. I have to say, take this row, which has only one thing in it, and dot product it with this column, which has only one thing in it. And that's going to give me the answer 3. And then I'm going to take this row, and I'm going to dot product it with this column, and that's going to give me a number 15. And then I'm going to take this row, and I'm going to dot product it with this column, and that gives me the number 6. And then I'm going to take this row, dot producted with each of those columns. That's going to give me 0 each time. And then I'm going to take this row, dot producted with each of the columns. And since that's 3 and this top one's 3, we already know the answer. It's 3, 15, 6, right? And so that's what we get. Bizarre. So you take x dot product y, and you get just a scalar back. But you take y dot product x, and you get this entire matrix, which is every combination of products of elements from y and elements from x. Fun fact. This, by the way, is called the inner product between two vectors. And this one here is called the outer product. So you will occasionally run into those terms. But that always struck me as extremely bizarre, that you would take two things and you get not only the different answer, but you get a completely different category of answer depending on which order you do it in. All right? Now, second thing that's a little bit confusing is this. Or maybe it's not confusing, but it's just kind of something worth knowing. Let's say I have a matrix A, we'll call it, and we'll make it a 2 by 3. Right, so we'll say 2, 4, 1, 1, 6, 7, whatever, right? Or I'm sorry, 3 by 2 is what I meant to say, 3 by 2. So this is a 3 by 2 matrix. And remember, the rules are I can multiply this by anything I want as long as it has 2 rows. Because if it has 2 rows, I can do this thing. So I can multiply this by a 2 by 1. I can multiply it by a 2 by 2. I can multiply it by 2 by 1 million. As long as each one of these columns of the thing, I can do the dot product with each of the rows, then I'm happy, right? Here's the interesting fact. You can't multiply A by everything because who knows how many rows the thing you're trying to multiply it has, or how many columns rather. No, how many rows is what I meant. But here's the thing: you can always do A dot A transpose. Remember, A transpose is the transpose of a matrix, meaning interchange the rows and columns. So if this right here is A, then that means A transpose is going to be a 2 by 3, which has all of the rows as columns instead of columns as rows, right? So we're just flipping them around. So here I have the first row being 2, 4. I'm going to say now I have the first column 2, 4. Here I have the second row being 1, 1. Here the second column is 1, 1, etc., right? So that is A transpose. And I can always do A transpose because, duh, if A is an m by n, then that means A transpose is an n by m. And the number of columns of the left-hand guy and the number of rows of the right-hand guy are the same as required. Therefore, this product does make sense. And it's also true that I can always do A transpose A for the same reason. Because then A transpose is going to be an N by M. And A, of course, is an M by N. Therefore, these two things are the same. And therefore, I can do this, this product here, right? And I get a different answer each way, right? So if A is a 3 by 2, like I have here, then A transpose, we're going to get a 3 by 3 answer. 3 by 3. Whereas if I do A transpose A, I'm going to get a 2 by 2 answer, right? So whenever I do a matrix times its transpose, A, I can always do it. And B, I'm always going to get back a square matrix. And the exact dimensions of that square matrix depends on how many rows the original guy had or how many columns the original guy had, depending on what order I do the things, right? Okay, now, last little group of surprising things here. Let me put some examples up just so we can see this. Because, again, this is easy to mess with you because you're so used to certain things being true. And there is particularly one of these that is not true with matrices like it was with regular numbers. And you can get into trouble if you assume it is. Because it's not. So I'm going to make 3 matrices here, A, B, and C, right? Now, the first thing I'm going to do is I'm going to say, let's compute A times B. And, you need some practice anyway, so let's go ahead and do this. So A times B is going to be the first row here, dot producted with the left column. So that's going to give us 8. And then the first row here, dot producted with the second column, and that's going to give us -4. And then the bottom row here, dot producted with the left column, and that's going to give us, I believe, 8 again. And then the bottom row here, dot producted with the right column, is going to give us -2, right? All right, now I'm going to compute B dot A. And what you're going to find is that B dot A is this row, dot producted with this guy here, which is going to give us 2. And right away, you can see why I'm showing this, right? That is not the same as that, which means no matter how the rest of this matrix turns out, this is not in general equal to this. The way we say that in math is that matrix multiplication is not commutative. If you take 2 matrices and you multiply them by each other, and then you multiply them by each other the other way, first of all, it might not even work in both directions. Now, in this case, it does because we have square matrices, and so both ways work. But in general, right, if you have to have M by N and you have to have P by Q, and you know that N is equal to P, well, it might be that N does equal P, but M doesn't equal Q, in which case you can't even do the operation the other way, right? But even if you can do the operation both ways, if you work this out, this is what we're going to get here. And those are clearly not the same. So you absolutely cannot count on 2 matrices being multiplied together in both directions and getting the same answer. Many times you can only do it in one direction and can't do it in the other. Sometimes you will get a different size thing if you do it one direction than if you do it the other. And sometimes you'll get the same size thing, but very often a different answer. And of course, occasionally you will get the same answer, but you certainly can't count on that in general. Right? So matrix multiplication is not commutative. That's your first surprising fact because you just had it baked into your brain for so long that, my gosh, if I take A times B, that's the same thing as B times A. I can just flip the order. Not so with matrices. All right? Now, next one I want to do here. What if I said I want to do, let me write this out. I want to do A times B times C. Now, let's do A times B first, and then do that times C. And we just did A times B, and if you remember, that was 8, 8, -4, -2. Okay, so now let's take that times C, which is 1, -1, -1, 4. And if you work that out, you're going to get 8 times, that's going to be 12. And then you're going to take this by this, and you're going to get -24. And then you're going to do this by this, and that's going to give you 10. And then you're going to do this dot producted with this, and that's going to give you -16. All right, very good to work that out and make sure you get the same answer, right? All right, so that's A times B times C. Now what I want to do is I want to do A times B times C. Okay, so it's the same operation seemingly, except this time I'm going to do B times C first. So if I take B times C, which is 1, 2, negative 1, 0, times 1, negative 1, negative 1, 4, and I multiply that thing out, so this right here is B times C that we're doing. I'm going to get 2, and then negative 5, and then 2, and then negative 2. All right, so that's what B times C is right there. And so now I'm going to take my A, 4, 2, 2, 3, and I'm going to multiply that by 2, 2, negative 5, negative 2. And when I do that, I get this times this gives me 12. And when I do this bottom row times the left column, notice sometimes I'm doing these in different order. I just kind of depends on how I feel at the moment. That's going to be 4 plus 6 is 10. And then I'm going to do the top row times this thing here. And I'm going to get negative 24. And then I'm going to do the bottom row times the right column. And I'm going to get negative 16. And lo and behold, we see that that is the same as this. And yes, it's true that this wasn't just a coincidental example. You can count on it. You can count on that always giving you the same answer as that, which means that matrix multiplication is associative. That's the fancy math word for meaning that if I take A times B times C, that's the same as A times B times C, which is important because it means that if we have a string of matrices that we're multiplying together, it does not matter what order we do the multiplications in. So it's weird, right? Commutative, you'd sort of expect to be true. That's not the case. It does matter which order they appear in left to right wise, the operands. But if you have a bunch of matrix multiplications stringed together, it doesn't matter which order you do the multiplications in. All that matters is what's on the left, what's on the right being the same. All right? Fun fact. So matrix multiplication is not commutative. Matrix multiplication is associative. And now the last one that I always just thought was kind of confusing, just not what I would expect at all, is what happens if you take two symmetric matrices and multiply them together. This actually turns out to be important for the work I'm doing now when I'm doing some social network analysis and modeling time series in an evolving social network. It turns out that the following fact is kind of crucially important. Let's take two symmetric matrices, and I think you'll agree if you look them over that A and C satisfy that. These are both symmetric. And remember, symmetric means they reflect along the diagonal. So that's the diagonal of a matrix. And for a 2 by 2, all that matters is that guy being equal to that guy. It's symmetric. And down here, that guy is equal to that guy, so it's symmetric, right? Remember, what it means is that, like if I have the matrix C, if C at a position ij is equal to C at ji, then that means it's symmetric for all the i's and j's in this thing, right? So it's clear that C11 equals C11, duh, that's hard to not be the case. C12 equals C21 in this case, right? It's not true for the B matrix, that's not symmetric, but it is true for the C matrix. And then C21 equals C12, and C22 equals C22, duh, that can't possibly not be true, okay? But really the key ones are those which are saying the same thing. And that is that, you know, the row I, column j has the same value as row j, column I. Okay, now let's multiply these two things together. I'm going to multiply A times C, and what I'm going to do is I'm going to say, let's take 4, 2 and dot product it with 1, negative 1, so that's going to give us 2. And let's take 2, 3 and dot product it with 1, negative 1, and that's going to give us negative 1. Now let's take 4, 2 and dot product it with negative 1, 4, and that's going to give us 4. And then let's take 2, 3 multiplied by negative 1, 4, and that's going to give us 10, I think. So the thing that's surprising is that that thing is not in general symmetric. And that really surprised me. I'm like, man, if you have two matrices that are symmetric, that means their rows and columns are interchangeable, right? So if you multiply them together, certainly you're going to get another symmetric thing, right? How can it not be? I mean, this symmetry says the rows and columns don't matter, so of course you're going to get an answer where the rows and columns don't matter. Not true. You certainly do not get a symmetric matrix in general, which always surprised me. I don't know if it does you.